law of conservation of energy and efficiency. Now, we have seen the law of conservation of energy before. Law of conservation of energy is this, that energy cannot be created or destroyed. It's just put in different forms. Now, we haven't mentioned a whole lot about efficiency. That's what I'm leading to here. Take a look at this roller coaster. You have at the very top, the cars are, well, it's pretty much standing still. It's going very slowly. You don't have a whole lot of kinetic energy at the top, but you have all kinds of potential energy at the top. So we've mentioned kinetic and potential before. If you were to add those two together at the top, it would be the same as it would be at any point during the ride. As you're going down, you lose some potential energy, but gain it in kinetic energy. And if you were to measure it way down at the bottom also, you would have the same total. It's just that it's placed differently as it was at the top. At the bottom, you'd have a whole lot of kinetic energy and not much potential energy. And that's going to lead to efficiency, because you are not going to have the same amount of energy put in as you get out. And what I mean is, if we were to let this roller coaster keep going and keep going, it would eventually, friction would make it want to slow down. So the energy cannot be created or destroyed still is true, but it kind of doesn't appear to be much, or it appears to be not as, say what the word I'm looking for, it kind of is harder to believe because of the force of friction. Now you know what friction is. We have friction whenever, oh, well, this guy right here, he's riding his bicycle and there is friction that makes the tires want to slow down. If he were to coast on his bicycle, the tires theoretically would keep going, but in reality friction is going to slow it down. So it appears that energy is created whenever this guy is pedaling, but it appears to be destroyed once this is stopped. But that is not true. Here this little guy is pushing the smaller guy, and the wheels eventually are going to succumb to friction when this guy stops pushing. Hopefully he's still holding on. But whenever he stops pushing, the wheels are going to eventually stop. It is channeled from one energy to another, and friction is probably best seen here, how it's channeled. We have this guy right here who is using two pulleys. Now let's say he puts forth however many joules of energy in which to pull this forward. He's going to lose some of that energy in the heat that ends up on these pulleys. These pulleys, because of the friction of the rope, is going to get kind of hot. So the amount of joules that he is using to pull this rope this way is not going to be the same amount of output that you get coming up. The input and the output is going to be different because of friction, and that's going to make imperfect machines. Sure, he's the one pulling this up, but it's not going to be the same amount of energy coming this way as it is this way. And like I said, it's not destroyed energy, as it's not created or destroyed. It just is burnt up in some of the heat that you're going to have in the pulleys. If you look at this kid right here, it's going to be the friction that will actually produce some heat for the tires right there. And same thing over here. You're going to lose some of that energy that way. And that will lead us to the efficiency formula. The efficiency formula is going to be output divided by input. Now this is always going to be less than 100%. Less than 100%. You cannot have a perfect machine where you put in the same amount of energy that you get out of it. It's just going to get less out than you have in. So if you're not quite sure which is the output and which is the input, the largest number is going to go on bottom. Hey, why don't we end up calculating a couple of these? Here we have piano on a steep ramps need 1600 joules of work to push it. In reality, 2500 joules of work is used to get it up the ramp. What's the efficiency? Let's go with output over input. That's what efficiency equals. So the output is 1600 joules over the input of 2600 joules and 2500 joules. Like I said, since you're always going to have something less than 100%, when in doubt, put the lower number on top and the higher number on bottom. So whenever you have 1600 divided by 2500, let's see what you will get. 16, and I know these will cancel out. I know these will end up canceling out, but just for the sake of explanation, I'll put 1600 divided by 2500, and that equals 64. Now, of course, you know that you'd move the decimal, and that would make it 64%. So, wham bam, we have found the efficiency of a machine, 64%. Now here we have the efficiency formula that we're going to have to change. You have output over input, but we're already getting the efficiency. So let's see what we're needing. We have efficiency, which is 40%. We have input, which is 150 joules. So we're going to have to solve for output. So I will multiply both sides by inputs. That will cancel those out. So we have output equals input times efficiency. Input times efficiency. So let's see what that turns out to be. Input is 150 joules times the efficiency, which is 40%. Well, that looks pretty straightforward. 150 times 0.40. Do you see why I got the 0.40? 0.40 because we had earlier made it had a decimal point, and now we'll make it a percentage. So let's see what that turns out to be. It turns out to be 60. Does that make sense? No. Drag this over here. Equals 60, and of course that would be in joules. So remember, you would have the input, which is bigger than the output. So we had 60 joules right here and 40 joules right there. See, does that make sense? Oh, my bad. It's not 40 joules, it's 150 joules. So output is 60, which is lower than the input, which is 150. Hey, so that seems to make sense right there. And you'll have some more of those in which to calculate in your book. Let's talk about something else. New technologies such as magnetic drains and microprocessors raise the machine's efficiency, but machines, just by definition, cannot completely eliminate energy leaking from the system. Now, I found this online. I presume that it has merit to it. But this is the percentage efficiency. And of course, none of these machines are at 100%, but some of them are getting pretty close. Looks like we have a bicycle here. The amount of pedal power you put into it is about 90% of what you get out of it. Or what you get out of it's about 90% of what you put into it. An electric motor, hey, that's very efficient. Looks like a diesel engine is not quite as efficient. That's what, 40%? Oh, so none of these are terribly efficient at all. A steam turbine, you can see, is this color. The human body, that's interesting, is about 25%. So the energy you put in, only about 25% of that comes out. It gets burned up otherwise. Gasoline engine is even less than the body and way less than diesel engine or electric motor. Then you have a steam engine, which is only at 10% efficiency. Now, the final thing I want to talk about is the word system. At the bottom, you can see we have a closed test tube and we have a fire. These are two different kinds of systems. Now, scientists use the word system to make studying these situations easier, as determining efficiency and so on. Now, you have a closed system right here. This is a closed system. Here, any kind of chemical reaction that goes on in here, some kind of fire, any kind, I guess it wouldn't be a fire because you don't have any oxygen in there, but any kind of reaction that two chemicals make together cannot get out. They cannot get out the top. So it is a closed system. Now, if you have a chemical reaction in here, it should weigh the same because you're not having any transfer of mass and you're not having any loss of energy. This is how it's in a closed system. Now, an open system would be like a fire here. Say you have a whole bunch of wood, a whole bunch of cardboard. It probably was stacked up pretty big at the beginning. Let's see, what can I have here? You might have had the cardboard stacked up to here. Now, once it burns, it appears that the cardboard and the wood just disintegrates down to nearly nothing. But what happens is you have a lot of the ashes, which are pretty dense. You have a lot of the fire, which sends things out into the atmosphere, and that would mean it abide the law of conservation of mass. And the same thing is going to be true in energy. You have some of the energy which is sent out past the system because it is an open system. And you know, it kind of makes it looks like energy is lost, but it's really not. You still have energy which is kind of used up, I guess you might say. Well, I certainly hope you've learned a little bit about conservation of energy and, more importantly, efficiency.